This lecture introduces the material in section 2.1 by explaining the consequences of the Earth's spin. The next lecture explains the celestial sphere and diurnal motion of the stars. The learning goals are to be able to explain the diurnal, that is daily, apparent motion of the stars and the sun due to the spin of the Earth, and to describe the celestial sphere and locate the north and south celestial poles in the celestial equator, to understand that the celestial sphere is an imaginary globe and physical distances to stars vary greatly, to describe the view of star motion as seen from the North Pole, the South Pole, and the equator, and at a mid-latitude location on Earth, to determine local time from stars, and to understand why the Earth spins and how you can prove that it spins. The first section of this learning module is about Earth's spinning motion around its axis of rotation. The axis of rotation connects the geographic North Pole and South Pole. As the Earth spins, the sun appears to rise in the morning on the eastern horizon, follow an arc across the sky, and set on the western horizon in the evening. A solar day is 24 hours. This is time that it takes for the sun's apparent motion across the sky, known as diurnal motion, to return to the position it had the previous day. The sun appears to move across the sky. It looks that way because the Earth is rotating on its axis. The axis is the imaginary line running through the center of the Earth between the North and South poles. The sun shines on the Earth. Half of the Earth has day, and the other half of the Earth has night. The Earth rotates one complete turn each day. We experience day and night because the Earth spins on its axis. Viewed from above the North Pole, the Earth spins counterclockwise. As it spins, we have sunrise, daytime, sunset, and night. At night, the stars appear to move counterclockwise in diurnal circles or daily arcs around the North Star for people living in the northern hemisphere. The North Star Polaris does not appear to move. Figure 2.7 in the book shows the time exposures for the sky, showing the apparent motions of the stars through the night. So they left the camera on a long exposure, and they captured this over maybe an hour or so, several hours. Note the difference in the circumpolar portion of the sky as seen from the two latitudes. From Canada, Polaris is high in the sky, and from southern Utah, Polaris is closer to the horizon. Also notice that the different stars have different colors. The apparent motion of the stars across the sky is a direct result of the Earth's motion, its rotation about its axis. If you were looking down at the North Pole, you would see the Earth orbiting the sun in a counterclockwise direction. You would also see the Earth spin on its axis in a counterclockwise direction. A satellite in geostationary orbit has an orbital period equal to the Earth's rotational period, which is one sidereal day, and thus appears motionless at a fixed position in the sky to ground observers. To have one ground station able to permanently point at the same sky location, communication satellites and weather satellites are often placed in geostationary orbits. This orbit is around the equatorial plane and is about 6.6 Earth radii from the center of the Earth. Considering the Earth's spin, the view on the left shows the view of the Earth from a geostationary satellite, while the view on the right shows an outsider's view of the Earth's spin synchronous with the satellite's orbit around the Earth. The first folder answers the question, why does the Earth spin? About 4.54 billion years ago, our solar system formed within a cloud of hydrogen gas when some shock instigated a local region of the cold gas to collapse inward due to its mutual gravitational attraction. Due to the conservation of angular momentum, As it collapsed, this cloud began to spin. So the sun and all the planets have spin to conserve that angular momentum. They still spin to this day due to inertia. This folder includes several animated videos that explain Earth's spin. Despite having a complete physical understanding of why the Earth and other planets in the solar system spin, and evidence from satellites observing the Earth, the notion that the Earth does not spin and rather the sun and the stars orbit the Earth persists even today. Had the ancient Greeks understood inertia, they probably would have concluded that the Earth spins. The next folder proves Earth spins. The consequences of spinning include the equatorial bulge, since Earth is not a perfect sphere, and the impact of something called the Coriolis force. The last lecture in this tutorial in how to do Observation Journal 3, the star clock, and this module ends with a self-assessment action video from the book. Some links in this learning module will help reinforce your understanding of why the Earth spins. The ancient Greeks could not resolve the difference whether the sun revolved around the Earth or the Earth revolved around the sun. They reasoned that if the Earth revolved around the sun, there would be parallax shifts in star positions. They were unable to measure the parallax because it is so small. They reasoned that if the Earth were spinning on its axis, a bird could not simply fly up into a tree, since the tree would be rotating while the bird was free from the Earth's bounds. The ancient Greeks knew that the Earth was spherical. Aristotle supported this claim with observational evidence. He observed the shape of the Earth's shadow on the moon during lunar eclipses. He also reasoned that the flat Earth, the profile of the ship, would shrink proportionally but remain the same shape as it sailed away. He further argued that on a spherical Earth, the bottom of the ship would disappear first, leaving just the mast as the last visible part as the ship departed. These observations led Greeks to understand that the Earth was a sphere. If someone asked you to prove that the Earth is spinning, rather than the sun and stars are orbiting the Earth, you could build something called a full cap pendulum and demonstrate Earth's motion. The Coriolis effect, which explains things like why hurricanes rotate and don't cross the equator, long-range bullets and missiles deflect in their path, and trains show uneven wear on the tracks, are explained by the rotation of the Earth. Some more effects of the Earth spinning include the flattening and Coriolis effect, and there are some YouTube video links in the learning module that will explain these in greater detail. Two things that are readily observable that demonstrate that the Earth is rotating again are that equatorial bulge and the Coriolis effect. There's a YouTube video explaining how fast the Earth spins. And now, how do we know how fast the Earth is really spinning? How fast are we moving if the Earth is spinning? This is how you can calculate this. You take a full circle, say you're standing at the equator. A full circle is 360 degrees. That's distance is the circumference, which is 2 times pi times the radius. The period of rotation is 1 day. It's 24 hours. So your angular velocity is 2 pi radians divided by 24 days. And your velocity is the circumference divided by the period, or 2 pi times r divided by the amount of time. It's just distance divided by time. So your velocity at the equator, if you plug in the numbers of 6371 kilometers for the equatorial radius of the Earth and 86,400 seconds for the length of a day, 24 hours, you come up with the fact that we're moving at 1,036.4 miles per hour. Now, if you're at some latitude, say Nashua, New Hampshire, you have to multiply that value by cosine of the latitude, because the circumference is smaller as you go towards the poles. Of course, at the North Pole, there's no circumference at all. You're just spinning on your axis if you could stand on the North Pole. While that's a very fast speed, I don't advise ever telling a policeman if he pulls you over and asks you if you know how fast you were going, that you say 1,036 miles per hour. All speeds are relative. They're all relative to something else. And when the policeman is asking you if you know how fast you're going, he means with respect to him as he is stationary on the surface of Earth, so that both rotational velocities are not part of his understanding of your speed. All motions are relative, and all events have both a time and a place. Earth spins on its axis once a day. The effects are the sun rises in the east and sets in the west. The moon and the stars also rise in the east and set in the west each day. It takes 24 hours for the Earth to rotate around its axis so that the sun is again at the same point. This period of rotation is called the solar day. It takes 23 hours, 56 minutes, and 4 seconds for the Earth to rotate around its axis so that the stars are once again at the same points. This period of rotation is called the sidereal day. The word sidereal comes from the Latin word for star. So here's a question to ponder. Why is there a 4-minute difference between the solar day and the sidereal day? We'll answer that later, but it's a good thing to start thinking about.